Hello class. In this section we're going to talk a little bit about the statistical reorder point and safety stock. So just as a reminder, here's our model of the inventory management systems delineated by random and deterministic demand, and this is our reorder point model. Again, just as a quick review, when demand and lead time are known, they're deterministic, which is the basic EOQ model that we discussed. However, if demand and or lead time are random, that is not completely predictable, then they are what we call stochastic models. So we build on the EOQ here, but we need to add safety stock. Our interest here will be looking at the distribution of demand during lead time. So when demand is uncertain, we try to estimate it with a probability distribution. We generally use the normal distribution, which is defined by a mean of mu and standard deviation sigma. So these models will give us the optimal safety stock level such that we minimize our stock out cost. We're not going to calculate how we come to that cost in this video, but we're just assuming that we're going to set some specified service level, which we'll talk about in just a minute. The reorder point model then is what we call a fixed order quantity system. And the continuous review, remember, that is where we review the inventory each time we withdraw an item and see if it's time to reorder. If we hit our reorder point, then we place our next EOQ order. And we still do that even if we have safety stock. So safety stock essentially just adds to our additional calculated reorder point. We use this inventory position to calculate these things. Inventory position is basically what's on hand plus the scheduled receipts and minus the units are on back order. So our decision rule then is whenever our inventory position hits the reorder point R, then we'll place the order for the fixed Q units. And so the purpose of this video then is to explore what that point R is when demand and lead time are. Under probabilistic conditions then, safety stock is the amount by which the reorder point exceeds the average lead time demand, and we're going to take a look at that. But first, let's talk for just a second about the service level. So the service level is usually stated in something like 90% or 95%. That's the probability of having a unit in stock if the unit is demanded. Therefore, the other component of it, alpha, is the probability of being out of stock. As you might know, since we're talking about a normal distribution, as we get further out into the tail of the distribution, our safety stock requirements go through the roof to achieve ever higher levels. So this is why, of course, we'll in practice never set a service level of 100%, but we have to find some medium ground. Quickly, the assumptions of our model are that demand is normally distributed, and we can use our EOQ model. The service level found in terms of no stock outs during lead time and reflected by a Z. And as I said before, our inventory position is reviewed continuously. Okay, let's take a look at this. We see the basic model that we're already familiar with of the reorder point. So let's imagine that demand varies, and in particular that it varies between lead time. So that is, this line, which now goes straight, could go maybe like this, like that, like this, like that. So we don't really know exactly what it's going to do. but we know that most of the observations will be around the line, which is the mean, which is our daily demand. So that means that we'll see that without safety stock, anytime demand drops below this line will be out of stock. So that means that we need to add this component, safety stock, down here such that we rarely go over. We already saw that we can't go over none of the time, so we need to establish essentially this distribution with the mean, and this area right in here would be our alpha, and the rest of this area would be our probability of being in stock. This is a probability of a stock out. Well, let's imagine for a second that lead time also varies. So here's our lead time right here. So let's imagine that we have a normal distribution around that with a mean mu and a standard deviation. So for that one, we also are going to want to set this space alpha, and which represents our stock out risk there. We see that demand and or lead time can vary. In case there's a stock out, and if they both vary, then we'll need to combine these stock outs. In any case, the general form of our formula is going to be this. Our reorder point R is going to be equal simply to the mean plus z times the standard deviation, which means then our safety stock is equal to z times the standard deviation, which is exactly the space in here. Here's a little nicer image of that if you'd like to explore this for a minute. And setting this thing up on its side where we can see it, first off, just assume that mu is equal to our average demand during lead time. And you'll remember from statistics that z, the standard normal variate, is going to be equal to x minus the mean over the standard deviation. Accordingly, from our formula that we just saw, x minus the mean is going to be our safety stock, this point right here. Now recall that this space is the probability of the stock out, and everything else is the probability of being in stock. This space, of course, then is z times the standard deviation, or x minus mu, and that's going to comprise our safety stock. Again, here's a little nicer image of these if you'd like to pause it and take a look at them. Okay, we're led to this formula here that the reorder point is going to be equal to the average demand during lead time, which is average demand times average lead time, plus the safety stock. We already know that safety stock then is equal to z times the standard deviation during lead time. So let's make an assumption that demand varies but lead time doesn't. In each of these days of the lead time, we know that we have exactly the same average demand with exactly the same standard deviation. We know that the standard deviation in the sequence of those events is going to be the square root of the sum of those variances. Essentially, then we add up the variance for each of those days and we take the square root of them. That gives us then the formula that we see here, where the standard deviation of lead time is equal to the square root of the lead time times the variance, the standard deviation of demand. So let's put this all together and then we'll work an example problem. So again, R is equal to the average demand during lead time plus the safety stock. If lead time varies, then in addition to our formula that we already laid out, which is our variance of demand times lead time under the radical, we then also need to add in the variance of the lead time times the average demand squared. Okay, now let's take a look at an example problem. I'll see you in the next video.